Okay. Morning, everyone. Last time we finished the 10.4. Actually, we did the area question and we did some examples. And like I said before, next week we will have a quiz. Okay. Okay, there. Okay. What is it? Okay. Yeah. Is that okay? All of you okay with the time? I mean, you are able to come, right? Or no? Okay. Not later. If later, then I need to discuss now today's case. Who? Three. So, or do you prefer the Monday? Between both of them.
Can we usually give it to the Monday and everyone?
No, I mean which day you can come.
Discuss with the president.
But I need to check schedule. I mean, I need to which day you are able to come. I will not give you a quiz. Is that okay? I mean, I need to know when you are able to come. Which week you can come? Which week?
It's not like official yet, so I want to make it official.
Can you make sure at the end of class?
Okay.
Okay. Yeah, and tell them to come to class. Okay. They never come to class. Okay, I need you to review the. I think this is from the parametric. I need you to try. Hopefully, you can do these two questions. Okay. I need to see how able you are to solve the problems. So the first question is asking the tangent and the concavity, and the second question is the arc length. I'm giving you maybe 5 minutes to solve, and let me know if you finish at least one problem you finish. Let me know. Raise your hand. So number one is find dy over dx and the second derivative for which value of t is the curve concave upward. And this is the parameter. And the second question, find the exact line of curve. This is the parametric equation and the t from 0 to 1. Yeah. Because it's only the up one. You need to divide that the absorbing. Because this is the input.
Udah sampai sesuai itu menunjukkan itu kita bahas
Apa satu?
terlalu satu bukan You find out the
You choose the eight equal to so you got 1% as well.
you keep going. Oh, because 1 plus time squared is 6. So I mean, t equal 10. T equal 10. So this equal cosecant square. Why not this one? Is this perfect?
One plus. Oh yeah.
Yeah, just do this simple. Maybe
This one.
So you can
Oh, okay.
Okay. For number 1, I hope you are able to differentiate or distinguish the problem on calculus 1 and now the calculus 2. In the calculus 1, we are only consider a single variable, right? Now we are consider the variable is they have chain rule reactions, okay? Which means we are actually relate the y and x, okay? The first one is this is the idea, the concept. You know this from calculus 1, but now both y and x, they are functions of another variable. We call the variable is parametric variable. It's t, usually t, but it can be also theta or any variables. And g also functions. So x and y is a functions of t. Okay. Now, if we are dealing with that and use some chain rule to connect all of this, what we are doing is just simply derive both x and y with respect to t and divide them, and we find the dy over dx. Okay? But to find the second derivative, this is quite tricky. We cannot derive from each of dy over dt and dx over dt. What we can do is we need to relate to our definitions, in which our definitions is y is function of x, and y and x is functions of t. So we need to include dy over dx in our calculations. That means okay. So this is quite important in parametric, okay? Because usually when you are seeing this pattern, initially what your mind is telling you to do is, okay, we can derive dy over dt, and we find the second derivative of dy over dt, second derivative of dx dt. And that is when you are going in the wrong path, okay? The wrong way, wrong way. What we should do is we need to relate all the y is actually part of x, right? Or x is the domain for y. That means we need to derive the first derivative of this part. Okay. So dy over dx, and then divide all with dx over dt. And that is the definition of second derivative in this case. Okay. Now we just see the x and y. Let's say x is t squared plus 1, y is t squared plus t. So dy over dx is 2t plus 1 and then 2t. Okay. Actually, you can solve this and make it 1 plus 2t. I prefer this one because it's doable, easy to calculate later. Okay. And now you are asking to find the second derivative. Okay. Now the top one, you will get -1 over 2t squared over 2t. Okay. And you don't need the quotient rule formula, right? You don't really need that. Now we have the second derivative, and concavity, we can check its concave upwards if, right? And to make it happen, our t should be negative. Because it has negative, and then constant. Okay? So we can conclude that from here, t should be less than 0. Okay. Okay, any questions first? Any questions? Now the second question is the arc length, or the length of the curve. So the second question, let me write the equations. X is 1 plus 3t squared. Y is 4 plus 2t cubed. And t is from 0 to 1. Okay. Before we are dealing with the formula for the length, we can find each first derivative for x and y. Is okay. And for the length, we can just write from 0 to 1, and then square root of okay. And then we can plug in the first derivative inside. Dx will be 36t squared and plus 36 t for dt. We can factorize 60. Okay. Now to solve this, we need some method from calculus 1. Okay. We can substitute this whole thing here. So du is 2t dt. So it will be 3 square root of u du, and u is from 1 to 2. Or we can solve this 3 wait wrong. So 2 square root of 2 minus 1. Okay. Okay, any questions? After these two exercise, I need to go to chapter 11. Okay, we can move from chapter 10 to 11. Okay. Okay. Let's move to the next page. Now, chapter 11 or 11.1, if we deal with the sequence. Okay. Sequences. And I believe most of you are familiar with the sequence. So sequence or infinite sequence is a list of number that written in order. We can write, for example, this is the terms that you are usually common in sequence. We are using A. Okay. A1, A2, A3, meanings this is the terms, the first terms, second, and so on. And we can also write all this list with this way, or this is also common use. But usually the left one, this one is commonly used in your textbook. And usually, like for example, okay, I can start from, let's say 1, 3, 5, 7. It has a pattern, right? We can say it's the odd, right? Or we can go from 2, 4, 6, 8. You can say it's even number. And sometimes you can write several formula for one sequence. Like this is, maybe you can write from n 2n minus 1, right? Or even when you are having the fractions in your sequence, for example, half this is usually 2n, right? And the fractions here, because the only thing that matters is the bottom one. We can write this as and sometimes we can make it more maybe I will write some really not really complex, but You can write like this also. You can see that it has specific patterns. The bottom one is from 5 squared, 5 cubed, and so on. But the top one is from 3, but then it's become negative 4, 5, -6, 7, right? And I hope you can do some, you can find the formula. Okay, I hope you can find the formula. Like you have positive and then negative and then positive and then negative. You can write the negative one. It can be n or n minus 1, depends which is the first alternating signs that appearing. Okay, you can write this, and then you can divide or you can separate the top one and the bottom one. So you can write that. And because it's always +1, we can just write the formula for this case is n just +2. Okay. And the bottom one, we start from 5, 25. It's all having ratio of 5, right? We can write 5 with the power of n. Okay. And all together, we can write the an. The formula for the sequence is -1 n minus 1 n plus 2 divided by 5 with the power of n. Okay, this is for all the sequence that have specific patterns, or you can find the patterns. Sometimes one sequence, like I said before, it can be having more than one formula. Okay, so it's possible. Not always specific like one formula, but it can have more than one. That's okay. But some sequence they cannot be defined like the like this special formula. Okay, so let me write some sequence. Doesn't have simple defining equation. For example, the population in one area or in the world. Like for example, PN, N is year end. Okay. And then maybe AN as the digit in the decimal place of E. Then AN is a sequence whose first terms we can say also this is a sequence, okay? Because E or pi, maybe pi, P or E, it has specific decimals, right? That is already it has the definitions. Okay? If you change the number, then it won't be the E, right? The Euler. Okay. So for some special irrational number, it is already a sequence that if we change the sequence, then the number definition will be changing, right? Okay. The third one is, I think, the famous one that you learned the first time you heard about the sequence. It's the Fibonacci, right? It starts from 1. And it has the definition. If Fibonacci is we call the Fn, then it will define recursively. Okay. So if F1 is 1, F2 is 1, and then Fn, we are having the concept Fn minus 1 plus Fn minus 2. So we need to plus the last number with the number previously. Okay. And n should be started from 3. Okay, that's just the intro for what is sequence. Okay, what is sequence? So sequence you can find in any places. Whenever you find a list of number, and you can find, maybe you can formulate some formula from that number, like maybe statistics, or maybe even if you are dealing with the database, like a data sheet, and then you find a pattern. Sometimes you can find the formula. Okay? And I think the sequence idea, okay, it's really useful when you are dealing with some simulations, okay, okay? And you need some tools to formulate the phenomenon. Okay, so that's the intro. Let me give you the second one. It's called the limit of sequence. So by the name of the title, limit. Okay, so we are dealing with the limit as in calculus 1. Okay, but what we change is we change the functions into a sequence. So we are treating this sequence as a function. Okay. Let me write the sequence, or we can plot the sequence. Okay, we can plot the sequence. For example, if the sequence is an and an n over n plus 1. Okay. Let me write some few terms. Okay. This is, if n is 1, then it's 1 over 2, 2 over 3, 3 over 4, 4 over 5, and so on. And if we are looking at the, let's say this is the representations for a sequence, like from 0, and maybe this is 1. Then if this is half, then this is A1, right? This is A1, A2, A3, and so on. And 2 over 3, maybe it's around here. And 3 over 4, maybe here. And 4 over 5, maybe here. And maybe here. And then it starts to getting closer. Let me make it bigger. So from the A1, and then A2, A3, A4. So as the, let me write here, as the n larger, or maybe we can say approaching infinity, then the value or the sequence closer to 1. right? From what you are seeing here, from what you've observed, okay? So it's getting closer. So by these observations, we can see that actually the sequence is getting a similar concept with limit, okay? And to graph the sequence, we can also plot the sequence in a graph that the axis is n and the y is the an. Okay, so if we are plot all the sequence that we can plot, let's say maybe until 5 here, and maybe 1 is here. Okay, it's not proportional, but it is to give you a good view for what is happening in the sequence. Let's say this is half, this is 2/3, this is 3/4, and it's getting closer and closer, okay? And you'll see that it's eventually getting closer to 1, okay? Let me write one more time here. Terms n over n plus 1, approaching 1, approach 1, as n becomes larger. And difference, the difference, okay, the difference one minus n plus 1, or we can say this is 1 n plus 1, can be made as small as possible by taking large n. So what does this mean? This means the gap in the graphs, the gap between the sequence and the value of 1 is getting closer. Okay, it's getting closer. Okay. So that intuitively, we can write limit as n approaching infinity, n over n plus 1 is equal 1. Okay. From these definitions. Okay. This is by intuitive. Okay. As you learned before in calculus 1, okay, limit. And limit means, okay, it's not the exact value. It's closer to something. Okay. So the sequence is actually never reaching value of 1, right? But it's really, really close to 1. That is the limit. Okay. So we can write a sequence an as limit L. You can write limit as n approaching infinity and L. Or we can say that an is getting closer to L as n approaching to infinity. And then remember also because of these definitions, the sequence N converges if the limit exists. And sequence AN diverges if the limit doesn't exist. Okay. But again, in limit, this definition is called intuitive definitions, in which you can observe some phenomenon and you can relate the phenomenon into the limit concept. Okay, we need to have definition that really can be proven. Can be proven. Okay. In calculus 1, you learn the precise definition of limit, in which you are learning the epsilon and delta. Right? In sequence, also similar. We can find we can write the precise definitions. Let me write one more time. Sequence AN has limit L. Okay. And then in precise definition, we are having the epsilon. If for every epsilon, positive epsilon, and epsilon should be positive. Like epsilon is like a distance, the gap. Okay? There will be corresponding integer n such that if the if n small n greater than the integer n, then smaller than epsilon. For example, if you have the sequence from 0 to some number, let's say just start with A1, but I will do like it has a pattern, but it's not really smooth like previous AN. Maybe the A2 is here, and then maybe going back here for A3, but then A4 is here, and maybe A5 is here, A6, and A7 here. And as the n getting bigger, it's actually getting closer to this value of L. Let me write L is here. So it's like here, 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 but then it's going. This is just a random sequence, but I want to show you that it's getting closer to L. Okay. And if we are zoom in, okay, let's say we zoom in and to visualize this epsilon, let me draw this. This means I want to zoom in the area nearby the L. Okay. Let's say it has the sequence here is AN plus 1. And this area is AN plus 2. Okay. Let's just say that. Okay. And this means the L minus epsilon, and this is L plus epsilon. Okay. And to note that the epsilon is really small. Okay. Okay. And you can also plot let's say this is L, this is AN, and this is N. Okay. Let's say the N start from let's say this is the integer N, and this is 1, 2, 3, 4. Okay. And maybe it's like this is L plus epsilon, and this is L minus epsilon. And another note I forgot to mention, we can see if you have this kind of sequence and this sequence, okay, you have two conditions on the right side. If it is increasing without any boundary, then it will be divergence. Okay, it will be divergence. And if you have this, it's like a sinusoidal, right? Going up, going down, going up, going down, and it also doesn't have which boundary, right? That the sequence will be stopped, right? This is also divergence. Okay. Okay, to conclude the precise definitions, okay, to conclude the precise definitions, let me write precise definitions of infinite limit. So limit as n approach infinity. If L is infinite, okay, it means for every positive m, let's define the m, there will be integer n such that if the terms n is greater than the integer n, then an is greater than the big M. So meaning it's getting larger and larger and larger. Okay. And similarly, if you have infinite limit in negative, you just make it mirror. Okay, so it should be less than M. Okay, for the negative parts. And please also, because we're dealing with limit, please remember all the property of limit, like the limit laws, the basic concept for limit. Okay, because I think I will not maybe really important for sequence. Okay. I'm just giving several examples that may be important, and maybe you will use it if you have a limit of a sequence, but you have a power like that. You can also so P should be positive and AN should be positive. Okay. Because if not, then if it's negative, then it will be switch, right? It will be a fraction. And also, I will review or giving you some theory on your calculus 1, because it also can be used in this chapter. It's called the Squeeze Theorem. Okay. Usually in your regular Squeeze Theorem, you are dealing with the functions, right? If you have functions, let me write the old terms. If you have limit, let's say x approaching infinity, if this is L, then okay, and somehow this is also applied in sequence. So if you have sequence that you can plot, and you can prove that AN less than BN and less than CN. For N, if you know the AN and CN, if both of them are approaching L, then the middle sequence will be approaching L as well. So this is by Squeeze Theorem. Okay. By Squeeze Theorem. Maybe if you plot both of them, you know that maybe one sequence like this, and maybe the second one like this, and maybe the other one like that. This is just illustrations, okay, to show that the sequence is correct or true, that it's between on the other two. Okay. Okay, that's the Squeeze theorem. And another theorem is if it is absolute value, okay, then let me give you some maybe example. Maybe to give you some idea of sequence first, okay? So, example, if you have a sequence, or maybe find the formula, find AN. Okay, maybe these two first. I think it should be not too difficult, right? Find the formula. So the first one is -3, and then 2, and then -4/3, and then 8/9, and -16/27. Number 2, the question number 2 is from half and then negative 4/3, 9/4, negative 16/5, and so on. What is the first sequence? What is called? What is called? It should be in your high school, I think. Right? But do you remember the name? What's the type? What usually you call the first one? Or you don't remember? It's called the geometric, right? Geometric sequence, right? So it's having A and then R, right? And then n-1. Right? So we can see from here the relations between the terms from A1, A2, A3 is you are multiply with negative 2/3. Right? Or no? Right? If you multiply, it's correct, right? So we can write the an is negative 3 and then negative 2/3 and n-1. Or do you have any other formula? I think it's too long. Okay, the second one, it's a combination of at least three sequence, right? The first is sequence of the alternating signs, in which you have positive, negative, right? So you can start by n-1. And then you have 1, 4, 9, 16, right? In which this is the n squared, right? And the bottom one is just 2, 3, 4. It's just n plus 1. So you can write negative 1. Okay. And what if you have the sequence 1, 0, so 1, 0, negative 1, 0, 1, 0, negative 1, 0. So this is n equal 1, n equal 2, and so on. Any idea? Any idea for this one? You have 1, and then 0, and then -1, and then 0, and then 1, and so on and so forth. Okay, so if you have, you see from all this sequence, the last one, the maximum one is just +1, right? The minimum is just -1. What kind of, yes, sine or cosine. So that's also we can conclude in sequence. So maybe I can write an, because the first one is +1. I can write sine and pi/2, right? If you have 2, its sine pi is 0, right? Or you can also write in the terms of cosine. So I need to modify to, yeah. So this is also can be, it's also a possibility. Okay? So whenever you find, like, you see 1 and the -1, probably it can be in a sine or cosine terms. Okay, that's just a review for the sequence. Let me go back to the limit and having some, for example, if your an is n over n plus 1, is the sequence converge or diverge? Okay. Of course, this is the previously graph, right? And we know that this is converged. But in terms of limit, we can write this as limit as n approaching infinity. And we solve them by our limit. Okay. So we can divide all by n, right? And we know that 1 over n, if we approach limit as n approaching infinity, it's 0. So we can say that it's 1. And also this already discussed at the early introductions, right? That the limit will be approaching 1. If you have n, converge or diverge, same questions. The same thing you can do is write the limit and then solve and divide by the biggest terms in the limit. Okay, so divide by n, it will be 1, and then this will be divided by n squared, and then, and from here is actually you will see that we will have 1 over 0, right? And in terms of limit, that's called the undefined, or we can say it's infinite, okay, or undefined. Or limit doesn't exist also correct. And if you have the another sequence ln n over n, okay, Same thing. You can write down. And remember, a limit, when you have conditions where your numerator and denominator is 0 over 0 or infinite over infinite, like this one, right? We can also use the L'Hopital rule. Yeah. Yeah. So it will be 0. So the limit exists and it's approaching 0. This is a little review for a limit part. Okay. And if you have an is e. We can write the limit as n approaching infinity. And then write e with the power of 1 over n. And because it's happening only in the power form, we can move the limit and write e with the power of limit n approach infinity 1 over n. So it will be e with the power of 0 is 1. Okay. Okay, let me give you maybe 2 more examples. And if you still have time, we can move on to the next sections. If you have determine if the sequence converge or diverge. So first, an is equal this is the first one. The second one is an cos squared n. Okay, 2 questions. Okay, so what's maybe the first one first? Should be converged, right? 0. This is converged. If you calculate this, it will be 0. Remember that if you have limit and approach infinity, if you have, for example, 4/9 and then n, it's 0. Okay, and this one, anyone solve? 0. Yeah. So to solve this, we can use the Squeeze Theorem. And we can start with writing down the and prove that because cosine having maximum value of 1, so it should be true, right? It should be true. And we know that limit as n approaching infinity of 1/2n, this is 0, right? And then cos squared n over 2n, or a limit, okay, limit terms. This also 0, and it's converged. Okay, I will continue and then maybe just a little bit and then we can finish. Let's another theorem is convergent if and divergent for all other R values. It can be 0 or 1. This is if this, and this is if R equal 1. I think this is just review for, I think we already did some calculation in calculus 1. And the other sections is called the monotonic and bounded sequence. I will just give you the definitions and then we finish the class. Okay. So definitions, sequence AN is increasing if the AN is less than AN plus 1. Okay. And sequence AN is decreasing if AN is greater than AN plus 1. This is for n greater than 1. This is also for n greater or equal 1. Okay. So meaning this increasing means A1 is the smallest one and then getting bigger and bigger. And this is decreasing. Okay. So we call monotonic. Okay, we call monotonic if it's always increasing or decreasing. Okay, we call it's monotonic sequence. So I think I will stop up until here. And okay, since I need to prepare for the quiz. Okay, so I'm preparing the next week, Wednesday. So anyone who else cannot attend next week, 17? 1, 2, and who else? 3? 3. When you can come to school after the 17th? Maybe Thursday. Okay. Okay, then maybe we still have the Wednesday quiz, and you will have another time. Okay. Okay. And I think we can finish up until here, and we will see you next week.